Okay, without further ado, I'll get started. As we said, my name is Michael Bali, and I'm presenting some thoughts on lunar navigation constellation design. Basically, I'm briefly going to talk about libration point orbits, distant retrograde orbit targeting and selection, and closed loop maneuver planning, NOD, and then a little bit on results. Really, the main focus of this presentation is the middle two bullets there, the DRO targeting and selection and closed loop maneuver planning and NOD, as I think those are unique applications of FreeFlyer that are pertinent to this sort of problem. And of course, as always, type questions into the question section, and moderators will help get to them. And so actually what I'm going to do right now is flip over to FreeFlyer and just kind of let this go while I kind of talk about the concept of lunar constellation design. So, as you've seen and as you know that, there's a rich design space and dynamical space associated with the cislunar region. In addition to low lunar orbit, you have all sorts of other three-body type orbits, halo orbits, near rectilinear halo orbits like we just saw from Diane's presentation, distant retrograde orbits, and L4 and L5 orbiters. And that's not even including things like Lyapunov orbits and the Lyapunov orbits and Lissajous orbits. And so when it comes to designing a constellation for navigation in cislunar space, there's really just a plethora of options that you have. And so the design space can be wide open, and you can do trades on relative geometry, tracking schedule, availability, and you can see in this video, I'm showing essentially link contacts between various pairings of satellites in all these orbits, and so the distance associated with the link, the amount of time any particular link may be available, all of those things are things that you can and should consider when designing a navigation constellation or any sort of constellation in cislunar space. For the analysis that I'm presenting, I chose a constellation of distant retrograde orbit satellites, mainly for their dynamical stability and the ability to provide stability of orbit without any sort of maintenance maneuvers. Whereas other halos will require maintenance maneuvers at varying frequencies, and so the other thing is they also provide a very convenient diversity of geometry for the NRHO orbits in particular, and that factors into the navigation analysis I did. And so as I get into the kind of mission design portion of the talk, one thing I want to mention is that actually for all of the orbits in this, except for obviously the low lunar orbit, which is pretty simple, and the gateway orbit that I'm showing, I used FreeFlyer's rotating pulsating coordinate system to target all of the DROs, all of the halos, and even the L4, L5 orbiters. And so, Brian next will be speaking about the two-level targeting method to convert from restricted three-body into an ephemeris system. But for simple orbits, I found that the rotating pulsating coordinate system is actually very handy with a targeter to generate these types of orbits. So with that, we'll switch back to my PowerPoint slides. And so, when it comes to constellation design, there's a whole lot to it. I've touched on some of it already. Station keeping, lifetime, coverage and contact, constellation sizing, and then on top of that, there's all the navigation design aspects in terms of tracking schedule and navigation accuracy. And, and one piece that probably would, often get neglected in, in kind of more sparsely populated orbit regimes, but conjunction analysis. Anytime you put up more than one spacecraft, there's potentially a chance for them to run into each other. And so, even that should factor into your design considerations. For the papers that I wrote, as I said, I used a constellation of DROs, and important in that process was finding stable distant retrograde orbits, and and picking ones that were useful and advantageous. And so what I did with FreeFlyer was essentially target a whole ring of 60 distant retrograde orbits shown in the upper plot, or the upper view, at essentially the same amplitude of distant retrograde orbit, ringed around in clock angle. And so those were all my initial candidates. And then to test for stability, simply propagated all those states around for 30 years, and kind of examined how they went. And so anything that left the vicinity of the distant retrograde orbit, or came in close contact with any of the other DROs, was rejected. And based on that criteria, 31 remained stable after 30 years. And you can see there's some kind of broad stability patterns, but there's no particular definitive rhyme or reason to why any one particular one was stable versus unstable. And from selecting these candidates, one of the other things I considered was, the long-term visibility of actually the DRO candidates with each other, so that they could potentially be used for interconstellation ranging. And so now what I'm going to get into in FreeFlyer script and focus on is how I did the distant retrograde orbit targeting using FreeFlyer's rotating pulsating coordinates, and how I used that to then create all the 60 candidates in FreeFlyer for selection. And for those that don't know, rotating pulsating coordinates is, it's a system that's very similar in design to the circular restricted three-body. But in this case, the coordinate system accounts for eccentricity in the secondary's orbit, in this case, the moon, by scaling the unit distance between the primaries, such that distance is always 1 and they remain fixed relative to each other. And so it creates kind of an odd conceptual idea of changing dimensionality in time. But in the Earth-Moon system in particular, it proves to be very useful when converting from idealized restricted three-body coordinates to real-world ephemeris. And so, oops, I'm getting ahead now. So moving over to the script example. So what I have here is really just a two freeform script. It's very simple, just create a few objects, and then set up force models and things. But really what I want to focus on is, as I said, the targeting of the distant retrograde orbit, and the setup of the rotating pulsating system. So actually, it's very easy to set up the rotating pulsating system. I just have it labeled here as RP. You set up its primary and secondary bodies, and for a standard setup, that can be all you have to do. There are a few other settings that you can change, but for Earth Moon, you can just set those and go. And the other nice thing is you can define a viewpoint for a 3D view based on your rotating pulsating system, with the initialize from rotating pulsating system method, where you just give it that, and then it defines the view based on that. And so then the way I seed my targeting loop is with restricted three-body coordinates, non-dimensional restricted three-body coordinates. So you have a rotating x, y, and z, and then you have rotating x, y, and z velocity, and yeah, these are not kilometers and kilometers per second; they're non-dimensionalized. And so I have a very simple FreeFlyer procedure that I use to convert the units, and it's a fairly simple set of equations. Just determine the characteristic length and mass of the system, and use those to convert the units into unitized kilometers and kilometers per second. And so then once I have those unitized coordinates, then I can go ahead and target my distant retrograde orbits. And so here I have a call to target just kind of the base initial one, and then I have a loop to go through all the DROs and phase them around to target them at different times, so that I get that nice ring of distant retrograde orbits. And so to go into that procedure where I target the distant retrograde orbit, it's actually a nested targeting procedure, but it's actually fairly simple. So I have two targeting loops, the outer and the inner. And with the outer targeting loop, I'm just adjusting the RLPX coordinate to get to the target half period that I want for the distant retrograde orbit. In the analysis, I used a near resonant DRO that's nearly resonant with the NRHO orbit, and so by adjusting the RLPX and targeting a delta T that was close to the half period that I wanted was how I got to that resonance. And then targeting to a stable distant retrograde orbit was done in the inner loop, where I varied the RLPY velocity and just using the rotating pulsating coordinates, took those those rotating pulsating coordinates, converted into, set it into the spacecraft state, and then targeted, step the spacecraft until I get to a plane crossing, the XZ plane crossing, and achieved, a zero rotating velocity at that time. And so then, this would continue to do that and then adjust for RLPX until I had both a stable DRO at the period that I wanted. And so then in my overall script, I just do that in a loop, kind of changing the initial time, based on essentially, whatever fraction of the overall time period I wanted to look at. And the end result is a ring of 60 DROs that are potential candidates for my constellation. So with that's kind of the usage of the rotating pulsating coordinates to target the DROs. And then the other piece that I mentioned is the closed loop maneuver planning and OD. And for anyone that saw Diane's presentation, the targeting for the NRHO station keeping is a bit more involved than your traditional targeting, and has the receding horizon approach. And so my mission plan for navigation analysis for NRHO utilize this targeting methodology. And it's convenient for a lot of reasons, one of which being that you have, for each maneuver you target, you have likely 6.5 revolutions or 42 days of stability ahead of you, which is a very useful concept of operations. So I utilize this full targeting scheme in my navigation analysis mission plan. And the other aspect that I think is really important for very high fidelity navigation analyses is having closed loop maneuver planning and orbit determination. You've got anytime you do anytime you actually fly a mission, you have this cycle that I've diagrammed on the right that is continually happening. You know, your spacecraft is flying. You've got some sort of dynamical error because no one's modeling all the forces exactly perfectly. That dynamical error paired with measurement error leads to navigation error. And then, you have to use a navigation state to plan your maneuvers. So there's some amount of maneuver planning error based on your navigation error. And then separate from your planning error, you actually have maneuver execution error, which then, of course, then feeds into additional dynamical error and navigation error, and around you go. And so, a lot of navigation analyses just, or I should say, a lot of maneuver planning analyses assume some kind of static level of navigation error. And while that's fine for a certain level of analysis, when you want to if you want to really, really mimic real-time operations scenarios, you have to be in a closed loop scenario. And with FreeFlyer, you can do that all in a single mission plan. It's very convenient. And so that's what I want to show with this. And kind of at a simple level, you can quantify the maneuver planning error fairly simply in FreeFlyer by simply planning each maneuver twice. Plan once with your truth state. That's your kind of true planned maneuver, and then plan it again with your nav state. And the difference between those two planned maneuvers is your maneuver planning error. And so it's very easily to quantify the impact of that. And so with that, I will again flip over to FreeFlyer and go into my NRHO navigation mission plan that is using a set of distant retrograde orbit satellites as navigation, a navigation constellation, and I'm using the NRHO. And I have this main loop here, which goes through 18 revolutions of the NRHO, and I ran this as a Monte Carlo to generate 50 cases per tracking schedule setup and the like. And I just want to kind of briefly walk through this loop. So basically the loop is kind of broken in, for each revolution, it's broken into a couple of different components. The maneuver planning section, which are these procedures here, maneuver execution right here, which is very simple. And then there is a propagation loop with some procedures for this steps down to Paraloon, applying disturbances to the Gateway spacecraft as it's dealing with all the puffs and coughs and wheezing that the spacecraft does when people are on it, simulates data, processes data, and computes relative state errors, and then collects some stats at periapsis, and then there's another while stepping loop back up to apoapsis, and collect some more stats up there, and then you just do that 18 times for 18 revs. But as I mentioned, the important part in my mind is the closed loop maneuver planning with this OD script. And so for this, it's really achieved with just two procedures, each called twice. So the first is, copying the estimated state from our NRHO nav into a planning spacecraft object, so that you have the full state covariance, all that. And then we have the planned NRHO station keeping, which does the receding horizon targeting, and computes the plan maneuver. And so you do that twice, where you have a plan maneuver and a truth plan maneuver. And then, as I said, the difference between those is simply your maneuver planning error. And so to go briefly into this, as I mentioned, this is very much the same. It's not identical to Diane's, because I'm sure she's continued to mature hers and add new constraints and things like that. But this is the same basic targeting algorithm. Trying to target out 6.5 revs. If it doesn't work, then fails down. If it doesn't work, fails down. If it doesn't work, fails down. And as Diane mentioned, it's very robust. And but definitely when you include all the disturbances associated with crude conditions on the gateway and those impacts on navigation errors, I did actually see some evidence of it becoming a little bit less stable, and I will point to that in a minute. But the important thing here is, as I said, you've got this full feedback between maneuver planning, navigation error, dynamical error. They all feed into each other, and either mitigate or reinforce each other. You never know depending on the situation. And after the maneuvers are planned, then the maneuver execution error is applied. And I want to show one brief thing about the maneuver execution error, because I think this is a kind of a unique usage in FreeFlyer as well. You can set a procedure that is based on just a thrust event, which is kind of the abstract base object for any type of maneuver. And so you can provide impulsive burns or finite burns, either or, and the procedure doesn't care. You can, and then adding a scale factor to the maneuver is fairly straightforward. You give some percent error and randomize it with the Gaussian distribution. But the pointing error, sometimes can be more difficult. And so if you go to the what I call this cone clock error, it allows you to very easily apply a pointing error in any reference frame, because you work from within the OD. There are thrust. There's a thrust offset delta X, delta Y, or a delta V offset delta X, delta Y, depending on, again, which burn type it is, finite or impulsive. But these are computed in the thrust frame. And so if you're using a finite burn that's using FreeFlyer thrusters and spacecraft attitude, you don't have to worry about spacecraft VCS. You don't have to worry about conversions from some lunar pointing frame, attitude frame to MENA J2000. You don't have to worry about any of those coordinate conversions. You can just do a simple random draw of cone and clock angle around your thrust vector, and do what amounts to a coordinate conversion to get from angles to a delta X and delta Y, which is shown right here. And then just apply those. And even though you're not doing any maneuver estimating, these offsets will get applied when executed within FreeFlyer. And so very simply, in just a few lines of code, you can have pointing errors that are applied to anything from a very simple impulsive delta V to a very, very high fidelity thruster bank and attitude dependent propulsion system. And the pointing error is derived from a simple parameter value of some 3 sigma pointing error and applied robustly regardless of maneuver type or maneuver complexity. And so with that, that's the extent of what I wanted to show in FreeFlyer script. To just, the focus of this isn't necessarily the analysis, it was really the script that got me here, but to kind of give you a feel for some of the results that I got, looking at different NRO and DRO constellations combinations, I compared to kind of your standard DSN tracking from the ground. And what I found was that because of the variable geometry, really any number of DRO constellations provided as good or better navigation results as the DSN. The DSN is in the upper right. This is plotting 120 days worth of NRHO navigation, position, and velocity errors, and their uncertainties over 120 days, 18 revs. And so you can see that clearly, even though this is only 2 DROs, it provided a better result in the DSN, and as you added more DROs, it got better, and with some kind of level of diminishing returns as you got more higher and higher in numbers of DROs. And also, the DROs could be used to navigate for each other. And so the DRO, in this case, actually, though, the DROs were only using the ranging associated with the NRHO spacecraft to do their tracking, but they could certainly track each other. That becomes a more involved, tracking schedule, but certainly, very easily doable. and the DRO orbits proved to be very stable over the whole time period as well. You know, the DRO and, you know, including DSN was also helpful, but, you know, definitely not required. And then finally, I think this slide shows, this is kind of what the thing I want to leave everyone with, which is, as I said, you know, closed loop maneuver planning can be very important. And this plot shows why, with a little bit of explanation. So of the 18 revs, there were 18 maneuvers applied. And generally, you know, and so this is all the Monte Carlo cases for each of those maneuvers with their maneuver magnitude. And so you can see for, and the blue line is the average of all the maneuvers at each point. And so you can see there's a spread of maneuvers based on how the Monte Carlo errors fell. But what's really important is a few of these maneuvers show bimodal distributions or multimodal distributions. In particular, the most extreme is maneuver 6, where you can see there's a group below 20 centimeters per second and a group around 80 centimeters per second. And that's just a huge difference. And you know, most of the other maneuvers don't really show that level of difference. The result, the reason is that was because of the NRHO targeting algorithm having to fail down to 4.5 revs rather than the full 6.5. And so because of that, and because of the way all the different puffs were accumulating, the planning didn't work well, and it didn't go to plan, and so it failed down. And you know, if you weren't doing a closed loop maneuver planning and OD simulation, you wouldn't have gotten that result. You wouldn't be able to necessarily see that. So to get to very high fidelity nav analysis, I think it's really important to include, you know, realistic OD and maneuver planning together. So clearly, you know, based on this, I would say libration points are the best orbits. And I think the rotating pulsating coordinates is actually kind of the Rodney Dangerfield of coordinate systems. It just doesn't quite get the respect it deserves. It's very, very handy for going from academic purposes to real world. And then, of course, closed loop maneuver planning and OD is very important for navigation and study realism. And then I also included just references for the relevant papers associated with my work in the area.
Thanks, Michael. We do have a couple of questions, and I want to get to them quickly. Is
Sure.
the origin of the rotating pulsating system the barycenter?
Yes, I believe so. I'll have to double check. It's either the barycenter or the primary, but I think it is the barycenter.
Great. Is there any standard mathematical technique to decide the initial RLP elements for a DRO orbit, especially when you're looking for stable DROs?
None that I'm aware of. I mean, it's with you know, restricted 3-body systems. It's fairly straightforward to compute families of distant retrograde orbits. You know, Diane's tool DST is very good at doing that. I myself would not say that I'm an expert. Like I said, I just kind of cherry picked a state from restricted 3-body system and just modified it to my own ends to get to. So there are definitely methods out there. They're usually in the restricted 3-body frame. In terms of stability, I don't think there's any real silver bullet to kind of being able to. I'm no expert in dynamical systems theory, so I could entirely be wrong. But I don't think there's any silver bullet to knowing stability. I think ultimately you just got to propagate it out.
Gotcha. You mentioned a closed loop process for both maneuver planning and OD. Are those done in the same mission plan? And could you also use the new optimizer in that loop if you wanted to?
I'm sorry, go
ahead. You mentioned a closed loop process for maneuver planning and OD. Are those done within the same mission plan? Could you use the new optimizer in that loop as well?
Yes, absolutely. Yeah, I mean, really, you know, in this mission plan where, you know, I have this plan NRHO station keep, that could be, you know, that mission plan could use an optimizer instead of a targeter. There's no difference there. You know, this This target using DC right here, that could very easily be optimization. There's nothing wrong with doing that. Absolutely not.